Hello, and welcome to this video on finding the area of a parallelogram by transforming the parallelogram into a rectangle. We'll get to use linear algebra to find the determinant of the parallelogram, and we will see how using linear algebra and determinants can help us with this task. So our parallelogram is determined by points -2, -2. So here we have the point -2 in x, -2 in y, then 0, 3, there is 0 in x, 3 in y, 4, -1, 4 in x, -1 in y, and 6, 4, 6 in x, and 4 in y. This is our parallelogram. We're going to transform the parallelogram into a rectangle. Now, the first thing we can do to get closer to seeing a rectangle is we can translate the parallelogram we have to make one of its vertices match the origin. So our first transformation consists of taking the parallelogram and translating it. This transformation takes vectors x, y, and maps them into x, y added with a vector. And because we want -2 to get translated to 0, that way the lower left vertex coincides with 0, 0, we get to add here 2, 2. Okay. When we do this, we obtain new vertices. So here we have that -2, -2 gets mapped into 0, 0. That's the idea of applying this transformation. Then the vertex for -1 gets transformed into 4, -1 added with 2, 2. So here we get the vectors 6 in x and 1 in y. And then the third vertex gets transformed into, so let's say 6, 4. Gets transformed into 8, 6. As we add 2 to x and 2 to the y component, that way we obtain 8, 6. And finally, the last vertex, 0, 3, gets mapped into 2, 5. Okay. So our new parallelogram is the same as the previous parallelogram, but translated. So let me show you a picture of that parallelogram here. After the transformation, we obtain this parallelogram. Later. Okay. All right. Okay. After we applied transformation T1 to our parallelogram P1, let's call this parallelogram P1, we get P2. And our parallelogram P2 is essentially the same as P1. P2 is P1 but translated. Then what we can say is that the area of P2 is the same as the area of P1. And we're trying to find the area of P1. So for now, we have a parallelogram in the first in the first quadrant, and we want to find the area of this parallelogram by transforming it into a rectangle. Okay. Now the next thing we want to do is we want to start making this parallelogram look like a rectangle. So we're going to apply a rotation to this parallelogram by an angle of minus theta, where the angle theta is the angle we see right here, the angle that is formed by the x-axis and one of the vertices of the parallelogram. Let's write the vertices of the parallelogram. Here we have 6, 1. Remember, this is okay. That was 2, 5. Then we had 8, 6. Okay. So the angle we use is an angle that satisfies that the angle is linked or corresponds to the point six, 1, and the transformation we need, our T2, is the rotation by an angle of minus theta. So this is denoted by transformation T sub negative theta. Okay. Then let's try to find T2. So T2 is given by this. And remember that when we work with rotations, we always go with the cosine of the angle and then the sine of the angle. That's the first column of the standard matrix associated with the rotation. And then we go with negative sine of the angle and cosine of the angle. Okay. And then because sine is odd and cosine is even, we can say that the transformation we're looking for is linked with the matrix cosine of theta, sine of theta, negative sine of theta, then cosine of theta, where theta is the angle that corresponds to the point 6, 1. In other words, theta is the angle whose tangent is 1/6. Or there's no need to write theta that way. You can just say theta corresponds to the point 6, 1. Okay. That's going to be our matrix associated with T2, but then to find this matrix more explicitly, we need to find the cosine of theta, where theta is this angle that is described here. And to find the cosine of theta, we work with a triangle. So this triangle has height 6 and width 6. If that was such a triangle and this is a right triangle, then the hypotenuse would have length root of 37. Then the cosine of theta, because theta is in the first quadrant, is 1/6 over root of 37. And the sine of theta, because theta is in the first quadrant, is 1 over root of 37. So then what we can say is that the matrix associated with our transformation 2 that rotates the parallelogram is given by 1 over root of 37. We can pull that root out. Every term inside this matrix right here has denominator root of 37. So this is going to be 1 over root of 37 times. Then we have 6, 1, negative 1, 6. Okay. Okay. Now with the formula for the matrix of the transformation, we find new vertices. So the new vertex corresponding to the right bottom. So there is 6, 1 is given by 1 over root of 37. Then we take matrix 6, 1 as the first row, negative 1, 6 as the second row, multiplied by 6, 1. This way we obtain 1 over root of 37, and then 6 times 6 plus 1 times 1, that gives us 37. And in the y component, we get negative 6 plus 6, so that's 0. Okay. That's the new vertex. The vertex after the transformation, vertex corresponding to 6, 1 is this vertex right here. Now when we apply T2 to the next vertex, so we go with 8 and then 6 in y, we obtain 1 over root of 37. And then the matrix 6, 1 is the first row, negative 1, 6 is the second row, 8, 6. So here we obtain 48 plus 6, that's 54. And there was a root before, 1 over root of 37, 54. And the other one is minus 8 plus 36, that's 28. Okay. So then we have that. And then we have the next vertex. And that's the vertex 2, 5. Gets transformed into the corresponding point. So that's 1 over root of 37. And we have our matrix. We're showing all details of how the vertices are getting transformed. So here we have 2, 5. This time we go with 1 over root of 37. Then it's 12 plus 5, that's 17. And negative 2 plus 30, that's 28. And T3 of the origin is the same as the origin because T is a linear transformation. So T maps the 0 vector into the 0 vector. I can write it here. That's because T3 is linear. And then with those vertices, we can map our parallelogram, and I have it mapped right here. Let me paste this. Now this is how our parallelogram looks like after the rotation. There we see differences between the parallelogram we started with and this parallelogram. Let's call the new parallelogram P3. And here we write P3. And now we wonder how the area of P3 is related to the area of P2. And we intuitively know that the area of P3 is the same as the area of P2 because we didn't change the parallelogram in any way, we just rotated it. But by using linear algebra, so here at this point we have the linear algebra part, we can say that the area of the transformed figure is the same as the determinant of the matrix associated with the transformation. In this case, that was square brackets T2 inside. This is an absolute value times the area of P2. Okay. Now the determinant of this matrix is the determinant of a constant times a matrix. Have 1 over root of 37, then 6, 6, 1, negative 1. And when we have a number besides the matrix, what happens is that the determinant of that resulting matrix is the number multiplied by itself as many times as the number of rows indicates. So in this case, we have 1 over root of 37 squared multiplied by the determinant of this matrix. That's because we're rescaling both the first row and the second row, and every time we rescale a row, the determinant gets rescaled accordingly. But we're rescaling both rows, then the determinant gets rescaled accordingly twice. So there we have this. And this determinant is 37. We have 6 times 6 minus negative 1 times 1. That gives us 37. And then divided by this 37, this gives us a 1. So there is 1 over 37 multiplied by 6 squared minus 1 times 1. This gives us positive 1. So our intuition tells us that after the rotation, there is no change in the determinant is confirmed. A of P3 is A of P2. And we got vertices that were, so here, got 37 over root of 37, 54 over 37 under the root. Here the height was 28 over root of 37. And this right here was 17 the root of 37. Okay. So there we have our parallelogram. And we're trying to, remember, we're trying to transform this parallelogram into a rectangle so that we compute the area of the original parallelogram by relating it to the area of a rectangle. And so far, we have applied 2 transformations. One of them is a translation. Another one is a rotation. Those are planar transformations. And the area has not changed in the process. Okay. Now the next thing we're going to do in order to exercise linear algebra and concepts from linear algebra is we're going to rescale the parallelogram because we see there's roots everywhere, root of 37 everywhere. We're going to rescale the parallelogram so we don't see those roots anymore. Because we did that, then we will be saying that we are going to apply a transformation. So here's a continuation. T3 that takes a vector xy and gives us the vector but rescaled by root of 37. So there we have the vector root of 37 times xy, meaning that this is the same as root of 37, 0, 0, root of 37, or if we want to say it this way, root of 37 times the identity matrix of size 2 by 2 times xy. When we apply this rescaling, we get to see a parallelogram that is very similar to the previous one. It's just that it's fully rescaled. Let's see how the area of the new parallelogram is related to the area of the previous one. So when we apply that rescaling, we get rid of those roots because each vertex gets multiplied by entries of each vertex get multiplied by root of 37. So now we get rid of that. And we get a parallelogram P4. Okay. But now the area of the parallelogram P4, so this is T3, is equal to the absolute value of the determinant of the matrix associated with T3 times the area of P3. Okay. So this is a determinant of root of 37 I2. So let's find it separately. Root of 37 I2. And because we have this number that shows up, like both rows of I2 are getting rescaled by root of 37, and the determinant gets rescaled every time. Correspondingly, then we get the root of 37 squared times the determinant of I2, and the determinant of I2 is 1. We do 1 times 1 minus 0 times 0. So here we get 37. So the area of P4 is 37 times the area of P3. Okay. So after we rescale all vertices by root of 37, the area is changing by a factor of 37. Okay. Now finally, what we can do to transform our parallelogram into a rectangle is we can apply a shearing transformation. And our shearing transformation is such that we want to see this inclined side of the parallelogram right here mapped into a vertical side. Let's see what happens when we do that. Now we're going to apply a shearing transformation. It's going to be T4. T4 comes from applying a shearing transformation that is like the one going forwards but backwards. You can see T4 as the inverse of another transformation. And the transformation going forward would be the one that doesn't change, 1, 0. but the one that maps this vector 0, 28 into the vector 17, 28. For such a transformation, we're thinking of mapping, according to the last bit we wrote, 28 times 0, 1 into 17, 28. So we can solve for t of 0, 1, because the 28 can come out, given that our t is a linear transformation, so constants can be pulled out. This equals 17 over, and then 28, not over 28, but the vector 17, 28. So we're thinking of asking for t to be mapping, to map 1, 0 into 1, 0, and 0, 1 into 17 over 28, and then 28 over 28. So that's this one over here. Okay. Then the matrix associated with t is given by 1, 0 in the first column and 17 over 28 and 1 in the second column. And because T4 is the inverse of T, then the matrix associated with T4 is the inverse of the matrix associated with T. And because this determinant is 1 times 1 minus 0 times something, the determinant is 1. And then we swap diagonal entries and change the sign. The entry of entries of the diagonal to get this. Okay. Okay. Now our new rectangle will look like our new parallelogram will look like a rectangle, and let's confirm that. So T4 applied to 37, 0. It's going to be 37, 0. Let's write it here. 1, 17 over 28, 0, 1, multiplied by, and then we have 37, 0. Here we get 37 plus 0 times something, so 37. Then 0 times 37 plus 1 times 0, so that's 0. And then we have T4. And because linear transformations map lines into lines, and it's enough to figure what happens with this vertex 17, 28. To see what happens with the whole parallelogram. So here we have 1, 0. And then 17 over 28, 1, multiplied by 17, 28. Oh, and there was a negative sign here, right? So it's 17 minus 17 over 28 times 28, that gives us 0. And then 0 times 17 plus 1 times 28, so 0, 28. So the picture we have in mind is looking like the following one. Okay, so here we have parallelogram number 5. It's actually a rectangle. 37, 0 was transformed into 37, 0, so just 37 here and 0. And then here we have 0, 28. And the other vertices will be mapped well 0, 0 into 0, 0, and the other vertex into 37, 28. And the area of the new parallelogram is the absolute value of the determinant of the matrix associated with T4, the transformation we used to go from P4 to P5, times the area of P4. But because T4 has a matrix that has ones on the diagonal, then the determinant is equal to 0. The determinant of the matrix associated with T4 is just, 1, not to 0. So this is equal to the area of P4. And here is the happy part. We can finally find the area of something, because this is a rectangle, so the area of P4 is width times height. So we have 37 times 28. Okay. So we found that the area after all this, we found that the area of P5 is 37 times 28. And at the same time, the area, and this was the same as the area of P4. Area of P5 is the same as the area of P4. Now the area of P4 is the same as 37 times the area of P3. So let's write that here. Let me write this line to have it more clearly. There you go. Now the area of P4 is the same as 37 times area of P3. But the area of P4 is the same as the area of P5, and the area of P5 is 37 times 28. So 37 times 28 is 37 times the area of P3. Then the area of P3 is 28. Okay. So we're going backwards. Now, the area of P3 is the same as the area of P2. And the area of P2 is the same as the area of P1. So what we can say is that the area of the parallelogram is 28. Area P3 is the same as the area of P2. Then the area of P2 is 28. And finally, the area of P2 is the same as the area of P1. Then the area we're looking for is 28. Okay. So this is how we can use transformations to find the area of a parallelogram step by step. This is all for this video. If you have questions, let me know. I'll be happy to help. Okay, we stop it here. And thank you very much for watching. Bye-bye.